Okay, let me start. Today we are going to keep going the lecture 10. So before starting, let's recap what we have done so far. So yeah, so in this lecture we've talked about the orthogonal projection, right? So in the last lecture, in lecture 9 maybe, we've talked about the orthogonal projection of a point in R2 space onto the line, right? So in this lecture we extended this concept to the general Rn space, right? So what is the orthogonal projection? So given a vector y and subspace W in Rn space, there is a vector y hat in W such that the y hat is the unique vector in W, for which the y minus y hat is the orthogonal to W, right? And y hat is the unique vector in W close to the y, right? So if you can see this figure, there is the one subspace W here, right? And there is another vector y outside of this subspace. Then what you want to do is to find out the projected vector y hat in the W space. So this y hat vector is going to be the unique vector. Then the y minus y hat is the closest the length between the given vector y with the subspace W. So this is the concept of the orthogonal projection. So why we need this? If you see this figure, actually in this course we are interested in the ax equals b, right? So in some case, we can find out the solution of the ax equals b, right? However, in some case or practice case, there are frequently ax equals c that doesn't have any solution. So this is called the inconsistent case, right? So in this case, we cannot find the exact solution of this system. So what I can do is to find out the approximate solution of this ax equals c, right? So if you remember this one, okay, let me say there is the input space Rn space, right? And output space Rm space. Then by using the matrix transformation A, we can transform this vector x to the ax, right? So in Rm space, if there is the point that satisfies the vector x, vector b is going to be the a times x. So that the set of those vectors are column space, right? So yeah, this is called the column space. But if we have some point c here that doesn't have any mapping point or the solution, that what we want to do is to find out the nearest point in the column space, right? So if we transform this column space W, something like this, and the vector C as a y vector y here, then what I want to do is to find out the new vector y hat in W space. So in the last lecture, we talked about how to represent this y hat in terms of the original vector y and orthogonal basis of the subspace W, right? So this is a very important idea to formulate the least square solution, which will be discussed in the lecture 11 maybe. Anyway, so in today's lecture, in the last lecture and today's lecture, we will introduce some kinds of the formulation to generate this orthogonal projection y hat by using the given vector y with the orthogonal basis of the subspace, right? Okay, so what was the orthogonal complement? So as you can see here, the orthogonal complement is the set of the whole vector z that are orthogonal to subspace W. So this is called the orthogonal complement, right? And here was a really important theorem called the orthogonal decomposition theorem. So let me say there is the subspace W in Rn space, and let me say we have the arbitrary vector y in Rn space, right? Then this vector y can be decomposed uniquely as y hat plus z, where y hat is in the subspace W and z is in the perpendicular W, right? So as you can see here, if we have the vector y here, then we can uniquely find out the y hat and z, right? So then how can we represent y hat here? So if we already know the orthogonal basis of the subspace W, then we can represent y hat with in terms of the vector y with the orthogonal basis u1 through the up, something like this, right? So actually, this formulation is really really similar to the formulation in lecture 9.1 maybe. Okay, let's go back. Lecture 9.2. 9.2. So yeah, here there was theorem in lecture 9.2 here. So as you can see here, if we have the vector y in W space, then we can represent this each y vector in terms of the orthogonal basis term, right? But in the orthogonal decomposition theorem, so we can generalize the previous theorem as y can be the any kind of the arbitrary vector in the Rn space. So, and then if we think about the y in W space, this orthogonal decomposition theorem will be exactly same as the previous one, this one, right? So this is the orthogonal decomposition theorem, and then we can say that this formulation is uniquely defined for each y and the W space, right? So by the way, until last week, until last lecture, we just think about we already know the orthogonal basis of the subspace W, right? But in next week, we will introduce the way to find out the orthogonal basis of the arbitrary subspace W. So, okay, let's discuss this next week. Anyway, so today, yep. So, and then there is another notation, orthogonal projection of the vector y onto the W space, right? So, which is written as the projection W vector y, right? So the question is how to find out or how to represent the y hat using the y and orthogonal basis of the W, right? So how can I prove this? Because the y1 is orthogonal to other orthogonal vectors y2 or y3 or the yp, right? Then what we want to do is to just compute the inner product between z and y1, right? Then we can decompose this something like this, right? Because the y1 inner product yj is equal to 0, so the remaining terms will be 0, something like this. So finally, there are y inner product u1 minus y inner product u1, right? So because those terms are same each other, so finally this z inner product u1 is equal to 0, right? So we can say that z is orthogonal to u1, right? Similarly, the z is orthogonal to each uj in the basis for the w for the subspace w, right? So we can say that the z is orthogonal to every vectors in w, right? Because every vectors in w can be represented by linear combination of the orthogonal basis, something like this, right? So that is in the perpendicular space of the W space, right? And how can we how can I prove the uniqueness of this representation? So let me say there is another representation y hat 1 plus z1 something like this. Then we can get this formulation, right? And because this y hat minus y hat minus y hat 1 is in the w, not only w but also in a perpendicular w, right? So we can generate the vector v, inner product of vector v is equal to 0, right? So in this case vector v should be 0 vector, right? So finally this proves that the y hat is equal to y hat 1 and z1 is equal to z. So in other words, there is only unique decomposition as a y hat plus z, right? So this is the proof of the orthogonal decomposition theorem, right? So, and there was example, something like this, right? We have the two vector u1 and u2 and another vector y, right? Then we can say that vector u1 and u2, the set of the u1 and u2 is the orthogonal base for the subspace w when w is the span of the u1 and u2. Then the question was that write y as a sum of the vector in w and vector orthogonal to w, right? So in other words, the question was to orthogonal decompose this y with in terms of the subspace w, right? So how can it that? Because we already know the formulation of the y hat like this, right? Then we can easily find out this term and this term by using the inner product, right? So finally, y hat was something like this, and what was the z, right? What was the z? Because the z here, z is the y minus y hat, so we can easily find out z, right? So in this case, the y minus y hat, which is z, right? So z is orthogonal to u1 and u2. So z is orthogonal to all of the w, right? So that is a perpendicular space. Z is in perpendicular space of the w, right? And then the vector y can be represent y hat plus z, like this, right? So this is the example, right? So and then we also discussed the geometry interpretation of the orthogonal projection, right? So what was the meaning of this term and this term? This term is the projection of the vector y to the this line, right? This line spanned by u1, right? And then this term is related to the vector y und projecting vector y to this line spanned by the u2, right? So the y hat should be this term plus this term, right? So this will be our final representation of the y hat, or the orthogonal projection of vector y onto the subspace w, right? So yeah, so if we think about the y in the w space, right? So in this case, orthogonal projection of w into the orthogonal projection of the vector y into the subspace w should be y itself, right? So this is the properties of the orthogonal projections. Okay, so today we will briefly introduce the best approximation theorem. So actually this theorem will be directly related to the least square theorem. Okay, so least square theorem will be discussed in lecture 11 and 12, but today we will just introduce the best approximation theorem. Okay, so let me start. Okay, here is the theorem. Let me say we have the subspace W in Rn space, right? And vector y in any vector in Rn space, and y hat be the orthogonal projection of the y onto W, right? Then y hat is the closest point in W to y. So in the sense that the length of y minus y hat is smaller than the length of the y. Okay, let me use the different color. So the length of the y minus y hat is smaller than length of the y minus v for other v in W distinct from the y hat. So what's the meaning of this theorem? So to understand this theorem, let me show the figure first. Okay, so let me say there is the subspace W, arbitrary subspace W here, and vector y here, right? Then we already know the y hat, the orthogonal projection of the y on into the W space here, right? Then we want to know this distance between y and y hat is the smallest distance between other case. So in other words, okay, let me say there is another point, the v here, then here, this is the length between y and v, vector y and vector v, right? So as you can see here, the length of the y minus y hat and the length of the y minus y hat is smaller than length of the y minus v, right? As you can see here, that the previous theorem proved that this term, this length is the closest distance among the every kind of possibility in the W space, right? So in this theorem, we will prove that this one is smaller than any kind of the vector distance with the vector v, right? Okay, so let me prove this one. Before that, we can say that vector y hat is called the best approximation to y by element of the W. Okay, so the best approximation means the errors between the original vector y with the approximated vector v in W space. So as I mentioned previously, what you want to do is to find out the best approximation to y by the element of W, right? So let me go back to deal with this limitation, right? So here, yeah. So the best approximation theorem means that the orthogonal projection y hat is the projection that we want to solve. Okay, so here the distance between y and v given by length of the y minus v can be regarded as the error. Let me say error of using v in place of the y, right? Then we want to find out the solution that minimizes this error, right? So in other words, this theorem says that this error is minimized when vector v is equal to y hat, right? So yeah, let me prove this one. So before that, there's one more property. This inequality 3, okay, let me say this is the inequality 3. This inequality 3 leads to the new proof that the y hat does not depend on the particular orthogonal basis used to compute it. So what does it mean? Okay, so Actually, this space Y can have the several kinds of the orthogonal bases, right? Orthogonal basis, right? By using this orthogonal basis, we derive the Y hat, right? Using where's that? This term, right? Because this is orthogonal basis, right? So in other words, if we have another orthogonal basis for the same subspace W, but we can uniquely represent the y hat by using the another orthogonal basis, right? So in other words, if a different orthogonal basis for W were used to construct an orthogonal projection Y, then this projection would also be the closest point in W to Y, that is Y hat, right? So in other words, by using any kind of the orthogonal basis for the subspace W, then we can find out the Y hat, right? So this is based on the best approximation theorem, right? So okay, let me prove this one. Okay, let's take another vector V here. Take a vector V in W distinct from the Y hat, right? And then Y hat minus V here, because this is Y hat, right? Y hat minus V is in W space, right? Right? And by orthogonal decomposition theorem, Y minus Y hat is orthogonal to W, right? We already know this, right? In particular, Y minus Y hat is orthogonal to Y hat minus V, right? Why? Because the Y hat minus V, this one, Y hat minus, okay, let me see. Y hat minus V in W space, right? In other words, this function this vector Y minus Y hat is orthogonal to every vectors in W space, right? So we can say that Y minus Y hat is inherently orthogonal to the Y hat minus V, right? Then Y minus V is equal to Y minus Y hat plus Y hat minus V. So what does it mean? Y minus V here is Y hat minus V plus Y minus Y hat, right? Because this is the triangular, right? So we can generate this one. And by the Pythagoras theorem, do you remember what was that, right? So by Pythagoras theorem, we can say that the scale length of the Y minus V here is equal to Y minus Y hat here plus Y hat minus V here, right? So this is the Pythagoras theorem, right? So what does it mean? So because the Y hat minus V, the scale length of the Y hat minus V is larger than 0. Y hat minus V here is larger than 0. Why? Because the Y hat is not equal to V, right? And because this is a scale length, so it should be larger than 0, always larger than 0, right? So inequality 3 here is follow immediately. Why? Because this is larger than 0, so we can say that when we compare this one and this one, this term should be smaller than this one. Why? Because this term is larger than 0, right? So by using this proof, we can say that this inequality is always true. Okay, so this is proof of the best approximation theorem, right? So okay, let me show some example. The distance from a point y or vector y in Rn space to the subspace W is defined the distance from y to the nearest point in W, right? So we already know this, right? And the question is to find out find the distance from y to W when W is the span by vector u1 and u2, right? Where y is something like this, u1 and u2 something like this, right? So yeah, let's solve this one. So first of all, by the best approximation theorem, the distance from vector y to W is what? Length of the y minus y hat, right? Where y hat is a projection, orthogonal projection of the y into space W, right? So why? Because this one, right? So in here, y hat is the closest point in W to y, right? So this is the best approximation theorem, right? So in other words, the discussion is to find out the y hat, right? Using the vector y and orthogonal basis of the u1 and u2. Orthogonal basis of the subspace W, right? Then what is the orthogonal basis for W? U1 and U2, right? Because the W is the span of the U1 and U2, right? So okay, let me find out the y hat, right? Okay, so first of all, y hat can be represented by, okay, let's go back here, or okay, let me show you here, right? So you can remember this one, y inner product u1 over u1 inner product u1 times u1. Okay, so let's go back. Okay, so this one is y u1 over u1 inner product u1, right? So what was the y minus u1? Y inner product u1. So -1, -5, 10, right? -1, -5, 10, right? It's like this. u1 is 5, -2, 1. 5, -2, 1, and 5, -2, 1, 5, -2, 1. So you can solve this one on other space, but I don't have enough space, so I just solve this one here. So please understand this. Anyway, so this term will be the -5 plus 10 plus 10 and 25 4 1, right? So it will be the 50 and with the 13 and will be the 1 over 2, right? Okay, so this term is 1 over 2. What about this term? Will be the y inner product u1 u2, right, over u2 inner product u2, right? So we already know the y2 u2 and y, so we can easily derive this one, right? Then here, from here, this, we can derive this one and this one, right? Then finally we can estimate this one, right? So we can easily derive this. Please do in yourself, because actually I already know the this one, but I already know how can we derive this one, but in your case, I think it is really important to derive this one yourself, because actually it's not difficult, but it's really important to derive this one. So please do it yourself, okay? And then what is the y minus y hat? So because we have to estimate the length of the y minus y hat, right? So from here, right? Because this is the distance, right? So y minus y hat is equal to y minus y hat. So it should be 1, 0, 3, 6, right? The scale length of the y minus y hat is equal to this one plus square this one plus square this one, right? So 3 square, 6 square, it should be 45, right? So finally, what is the distance from y to w? Because there is a square term here, so we have to use the square root here. So finally, 3 square root of 5, right? So this will be the distance from y to w, right? So in geometrical view, okay, let me say there is a w here and vector y here. Then what is the distance between this vector and this subspace w? It can be defined by orthogonal projection y hat here. So in this case, the length between this vector y and subspace w is 3 scale to 5, right? So this is the solution of this example, right? This is also very intuitive and easy, right? So you can easily follow this one. Yeah, here is one more theorem. Actually, this theorem is not a new theorem. This theorem is closely related to the previous one. Okay, so let me say we have a also normal basis u1 through the up. Here it's not a orthogonal, but it's also normal basis. Also normal basis for the subspace W of Rn. So what was the difference between orthogonal basis and also normal basis? What was the difference? What was the difference? The orthonormal basis means the length of each base vector is 1. So it means that yi inner product yi is equal to 1, right? Because the length of this unit vector vector is 1, so this vector u1 through the up are the unit vector, right? So in this case we can also represent the y hat by using the vector y and also normal basis, this one, right? But what was the difference? If you remember this representation, there was term something like this, right? But as I mentioned before, if the y is the also normal basis, y1 inner product y1 should be 1, right? So this term should be 1, so this term will be remain, right? So in other words, the y, let me throw here, y1 inner product y1 is equal to 1, right? So we don't need to consider this one, right? So the remaining part is y inner product u1 times u1, y inner product u2 times u2 plus y inner product up times up, right? So we can say that if we have the also normal basis for the subspace W, then we can represent projection of the Y onto the subspace W is something like this, right? So this is another theorem. So in other words, if the Y if we have the vector matrix Y that has the also normal basis as a column vector, something like this, right? Then we can represent this one in terms of the matrix multiplication, right? How can we do that? So this one is going to be Y times Y transpose matrix U times U transpose times vector Y for every Y in Rn space, right? So in other words, we can represent this vector equation as a matrix multiplication. So let me derive this one. Actually, this is very easy to describe this. Okay, so first of all, let me say, yeah. So let me say this is the equation 4, and okay, let me say this is the equation 5, right? So equation 5, right? So first of all, the formula formula 4 here, just follow immediately from 2 in the orthogonal decomposition theorem, as I've shown this one previous slide, right? And also the formula 4 shows that projection of Y onto the double space is the linear combination of the columns of the matrix U using the weight this one y inner product U1, y inner product U2, and y inner product UP, right? As you can see here, this is a vector, right? This is a vector, right? This is a scalar value, right? Because this is the output of the inner product, right? Then what does it mean? We can represent projection of y into the W space as a linear combination of the vector U1, U2 through the UP with the coefficient y inner product U1, y inner product U2, y inner product UP, something like this. So this is a linear combination of the columns of U, something like U1, U2, UP, right? With this one as a weight, right? So this weight can be written as this one, right? Right? Because this inner product just represented by the U1 transpose times Y, right? Like this, showing that they are entry in the Y transpose Y, right? So this linear combination first can be represented by U, because the vector okay, let me draw something like this. U1, U2, UP here with the weight term Y, U1, Y, U2, Y, UP here, right? So yeah, let's use this one. So actually this is the Y1 transpose U1 transpose Y, U2 transpose Y, and UP transpose Y, and this is just Y vector matrix U here. So and this one is just U transpose Y here, right? So in other words, this term, this linear combination can be represented by matrix U times U transpose vector Y here. So in other words, the projection of vector Y into the W space can be represented by U times U transpose times vector Y, where the matrix U is the matrix U consisting of the also normal basis as a column space or as a columns, something like this, right? So we can represent this one as a U and Y with this formulation. Okay, so yeah, this is the end of the today's lecture. In this week's we introduced the also corner projection concept, right? So in the following lecture, we will introduce Gram-Schmidt's decomposition method to find out the orthogonal basis of the arbitrary subspace, and then by using those kinds of concepts, we will derive the least square solution. So least square concept and least square solution. So least square solution will be popularly this solution has been popularly used in many kinds of the application or the problems, right? But comparing to the system that has the exactly one solution or the just solution, most of the practical system doesn't have any solution, right? But by using the least square solution, we can get the way to find out the approximated solution for those kinds of the linear system. So okay, let's think about what is the least square solution for those problems. Okay, so this is the end of this lecture. See you next week.